guys' preference for your teammates. The rest of the class demonstrate no preference, so I just randomly assign you to some group. Hopefully, you won't have any problem to work with your teammates. So for the group case study, I hope everybody's here. You want to first get familiar with your teammates after today's class, or as late as Wednesday's class. Everybody should be here. And if you until Wednesday still some teammates never show up in these two classes, let me know. I will contact him first. Make sure he know or she know that she or he is in the group, has responsibility. So the due dates for the reports and presentation is next Wednesday. So you can begin to do that before the October break, or push yourself very hard after October break. It's your choice. It's a team choice, right? And 5 pages, minimum is 5 pages for the reports, and the presentation is about 8 minutes. Everybody has to prepare the past he or she has to present. So everybody come to here to present. Okay, not just stand here. Any question for the case? Group case study? No? Everybody's good? Okay. That's good. So the case study cover the content from chapter 1, 3, 5, 8, and 10. So last group, you have to do the case study for this chapter. That's fine. We'll finish this chapter most likely this today, but the contents you need for the case, we already finished last week. So you should have all the knowledge you need for the case study. Okay, so last week we have begin our journey about quality control. Well, to control quality, the most important thing we'll learn in this chapter is to build a control chart. Okay. Without control chart, we can talk about human resource. Okay, motivate your human resource, and then they can have a better quality. When talk about customer satisfaction, we just react fast, then the satisfaction will improve. But those idea, great idea, but that's no standard. So when we talk about service or product, there are lots of standards, right? Like gas per, miles per gallon, like how do you say the pedonal value and the complaints range, how many dents we have by the used car. So that's why we need to do control charts. To build control charts, first is the mean charts, and the second is the range chart to monitor our performance. And the last part of last week's class, we entered into the control charts for attributes, which are P charts and C charts. So we have gone through an example of P charts. Well, we can classify our observation by either good or bad, pass or fail, or works, doesn't work. So here's the formula to build a P chart. We need to first calculate standard deviation of the proportion, sigma hat P, square roots P bar times 1 minus P bar divided by N. And then go ahead to build the upper control limits and the lower control limits for the proportion charts. And we went through this example to build the control charts. Pretty straightforward. So P bar here is 4%, 0.04. So use 0.04 times 0.96, which is 1 minus P bar. Take the square roots divided by 100, you get sigma hat P, and then go ahead. You can build the control charts. So last control charts we're studying this chapter is called C charts, count charts. So C charts can be used when the number of occurrences per unit of measure can be counted. Right? Non-occurrence cannot be counted. For example, if we see a car, how many scratch, chips, dents, or arrows? Okay, we see some furniture, how many cracks or faults per unit of distance or square feet? And breaks or tears per unit of area. And then we talk about biology or public health. The bacteria pollutants per unit of volume, and how many calls, how many complaints only per unit, like per hour, per week. Right? So if we measure our performance by the count, how many occurrences happen, how many complaints happen, well, we don't go deeper to say, okay, one complaint is really a huge complaint, one is like minor complaints. Right? That's a different story. Right? That's pretty complex. But if we trace their equal, so similar like dents, that can be a big dent or a very tiny dent. But we trace them equal, or think they're pretty similar to each other, then we can use this C-chart to control the quantity. So here is the formula to build a C-chart. It's very straightforward. Upper control limit C is equal to C plus Z value times square root of C. Lower control limit C is equal to C minus Z value square root of C. Okay. So let's do the example together. An inspector found an average of 3.9 scratches in the exterior paint of each the cars being prepared for shipment to the dealers. We want to use the C-charts to determine a 2 sigma. So it's 2 sigma. So now what is Z value? 2. Right? Determine the 2 sigma control limit for this problem. So first, we know that's probably like a C-chart, but if we finish this chapter, I give you this as a homework. You should think about, okay, which chart we should go. Okay, you can see average of 3.9 scratch. So scratch, how do you measure scratch? It's not continuous. It's 1, 2, 3, 4, 5, right? So it's by count. Then we think, oh, that's if we want to measure the performance of how many scratch, then we should go to C charts instead of mean, range, or even proportion, right? So we should go to C charts. So I'll give you guys 5 minutes. Should be more than enough to solve this problem.
No, we're just answering.
He's the only boy.
Yeah.
Don't spoil him. We have the gender equality, right? So if you guys bully, let me know. I find out it has to show up on once, otherwise nobody knows it. Okay. Missing the class.
Just 3.9, and then your sigma is 2. It's the Z divided by.
So easy, right?
That's why it confused me almost.
Why are you confused? Too easy? Too easy to be true.
Math is never easy.
No. I test my daughter like 3 point plus 5 every day, so. She complains. She still complains. Anything more than 10, she complains. Done? That's finished. Let's just forward. Finish. Okay, good. Okay, so I have seen, in fact, 3 minutes is enough for many of you guys. So, who can tell me how to build the upper control limit for the C charts? Anybody can tell me? Upper control limit. UCL.
You plug in 3.9.
3.9, which is C, the occurrences, plus
2
2
square root,
square root
then 3.9.
3.9. What's the final result?
7.8. We're not 7.
7 points. Everybody got 7.8?
Yes.
Okay. What about the lower control limit? The same? Minus 2 times square root of 3.9, you should get 0.05, is that right? Huh? Right? Okay, now we have this control chart. Always remember, control chart is just a tool. If you don't know how to use the tool, still, you can't do a very good job on the quality control. So after we build this control chart, how can we use this control chart in the future? How will we use this control chart for the future? To control our quality. What's the purpose? We spend 3 minutes to build control charts for fun. 0.05 to 7.8. How it can be used for us to control our quality? It's a hard question. Or too easy, nobody wants to answer. We have this range, right? So we spend some time to build a control chart. But how do you use this chart in the future? Next week, we have to send cars to the dealers again. Should we do the inspection? If we do the inspection, then how do you use these control charts?
If there's any more than whatever the upper limit is, you don't send them out.
Yeah. Probably not send this out, but we have dig outs, right? So maybe apologize to a dealer. This time, okay, it's out of control. We have to find why, transportation problem or maintenance problem. Or similarly, anything more than 8, right? More than 8 average. When we talk about this, that's average, not just one car. We every time we send like 100 cars to dealer, we check maybe 10 cars to see the average. If average more than 8, like integer number, right? Then we think it's out of control. We should do something. We should at least dig out. Whether it's our transportation problem or maintenance or some kids just play around and then have some scratch, or if it's 0, right? Lower than the lower control limit, if it's 0, we should also dig out why. If it's 0, it's not pure lucky, because you can see that if you're like 1, probably that's close to the lower control limit. You accept that, you perform very good. But if it's 0, you learn, okay, what's the lesson we can learn? Maybe this transportation, we use some special protection, or maybe we train our employer in our manufacturing place. Then you also want to find out why it's so good. But the most important is anything greater than 8, you should raise big concern. Okay? So we have finished all the 4 major control charts we want you guys to know and use in the future. For managerial consideration, to use the control charts, we have to think about what point the process to use the control chart. It's similar to the discussion we have there when to do the inspection. Well, for example, you want to use the control chart for the raw material. You receive raw material, you want to check the raw material. You definitely want to use the control charts like the previous example before you ship to dealers. Otherwise it's too late to change anything, right? So there's 2 parts. Before you begin the production or before ship to customer or your downstream player, you definitely want to use control chart. In the middle process, you can also think about some important step. You can use the control chart. Sample size. What's your opinion? What size of sample you take? Sample size.
Depends.
It depends. Yeah, it depends. But have you guys learned some number? Remember some number or roughly number? We should go for the sample size.
10%.
20 to. Kira is very good at memory. I think we mentioned it 20 to 25 in last week's class. Some
No, I
place.
just wrote it down today.
Oh, you have wrote down. Okay, that's good. I have to withdraw my praise on you. So 20, but good notes taking, right? So 20 to 25 is the sample that we mentioned last week about build the mean charts, right? But you should also remember a magic number you have learned in statistics class. Dr. Richard, Victor, Visual. I don't know whole tissue, but we have so many faculty, right? Do you remember any magic number when we talk about sample size in the business statistical?
30.
Very good. Well, I have several students remember this magic number is 30. 30 is really magic number, right? And I don't know why. I mean, I know why, but I can't explain why to you guys. Or otherwise, we'll spend probably we have spent half of semester to explain why this is 30. Because it's the central limit theory. It's one of the fundamental theory of statistics. So you think about long time ago, statistics is just a branch of math. And then it's become individual subjects with central limit theory or some other theory. So central limit theory think about, okay, if you collect samples that large and large enough, the sampling distribution will follow the normal distribution, which is the same distribution with the original population. Otherwise, for example, if you only choose one sample here, one student, like we choose Alan, right? Then anything we get from Alan can't represent the whole group. Agree, right? Same if we choose Kayla, not enough. But if we choose 10 students here, about 1/3 of population, most likely, okay, this sample, 10 students performance average, heights, weights, GPA, probably very similar to the whole group of students. Right? So that's the idea, central limit theory. So by the central limit theory, people study, and get the 30 is a magic number, which is not a theoretical number. This is the experience. Even we have this theory can't tell us. This theory only tell you the more the better. It didn't give us a threshold. So it's by a long time experience, people think 30 is enough. Again, the more the better. But if you get 30, should be pretty confident. You get 20 to 25, it depends. Just can use that. Or you can try your hard, try the best. You get as many you can. But any number more than 30, you should feel a little bit comfortable. All right? Sample size. Sample frequency. So that means when you want to collect sample again and again. Some company did that like every day to collect sample in production line every day. Some maybe once per week, once per month. It really depends on how frequent you want to monitor or you want to update your control charts. The last question we have discussed is 4 different types of control charts. Who can tell us what are the 4 control charts we have studied so far? We have learned 4 different control charts. What's the first one? First control chart we have learned.
X bar.
X bar mean charts, right? X bar, X chart in fact. Second range, very good. Third one. Who is the third one? Last Friday, P, proportion chart. The last one, everybody should know the last one. C, C chart, right? So you just remember mean and range belong to the variables, which means it can be measured continuous, right? We talk about means can be 3.5, 6, 7, 8, 9, right? Something like that. But for the P charts and C charts, proportion and cons, it's not measured continuous. Proportion is always between 0 and 100%, right? C chart is most likely is positive integer number 1, 2, 3, 4, 5, 6. So then it depends on your products or service. Then you choose which control chart to use. Control charts can't solve or discover all the problem for the quality. We'll see why. Okay. Even a process appears to be under control, the data may still not reflect a random process. We have learned in chapter 3 too, but you will see here again. Analysts often supplement the control chart with a run test. So the run test is a test for patterns in sequence. Run is a sequence of observations with a certain characteristic. We won't go to detail, okay, how to calculate a run test. You should read it by yourself in the textbook. But let's see some pictures to understand why we need the run test beyond the control charts. The first one, right? We have see something very similar in chapter 3 when we study the forecasting. Right? What is the trend of this time series plots? What is the trend? Increasing trend, right? Yeah. So it's under control, always under control. From very close to the bottom line, lower control limits, to the upper control limit. But we do have a concern if you see something like that. Finally, it will be above the upper control limit because the trend is pretty obvious. But the control chart can't tell you this problem because every point is under control. Similarly, cycle, right? We have learned that a lot in our homework, chapter 3. Right? We see some cycle. It's still under control, but there's something wrong. It can happen. One obvious example is like night shifts, day shifts, night shifts, day shifts. Their performance is like that. Then you should think about why the night shift and day shift has this gap. Every speak. BIOS is always close to lower control limit. Well, customers don't like that. If you claim your mass getting 30, it always gets 29, 28. Well, long term is not a good thing, even it's still under control. The last one is too much dispersion. Everything's under control, but it's not very close to the mean. It's up, down, up, down. So you should also raise your concern. If you have time, you want to dig out. The last topic we'll talk about in this chapter is about the capability. Once the process has been determined to be stable, think about your parking skill. Once it's stable, then we have to determine whether you are available, you are eligible to park in the downtown area. Okay. To determine the process capable of producing something within an acceptable range. So acceptable range, we also call it tolerances or specification, which is the range of acceptable values, either designed by an engineer. Say we want to produce this computer. What is the length, the width, the thickness of the computer, right? Or nowadays, more and more by customer. I want to satisfy your order. Then I want to satisfy your requirement. Even it's totally new requirement, we try to satisfy. Every process has a variability. We have talked about that, right? It's a natural or inherent variability. Process capability is to the variability of process outputs relative to the variation allowed by the design specification. Let's see what is the process capability. Here. So there's 3 pictures here. So the first one, do you think this process is capable to satisfy this lower and upper specification? The first one, capable or not? I always ask you before I teach, right? That's not good, but yeah. I definitely will teach you guys how to see the picture. But first, just use your common sense or business sense. Sometimes. But we have to make the conclusion whether it's capable or not. You can't say sometimes.
Well, that like depends on like what your variables are.
Variable.
I mean, like it's like where you are on the chart.
Yeah, I understand what you mean. You have similar idea with Kayla, but we know that okay, this is customer requirements, right? Customer only allow this lower specification to upper specification. This is our performance. Not good? Capable or not?
No.
Not capable. Because we have a big probability out of control, right? So it's not capable. The last one, capable or not? Capable? No? Not capable?
Yes.
Yes. Because control limits, lower specification and upper specification are further of your process variation. The tricky part is this one. Exact match the lower tail and the upper tail. What do you think? It's cut on the edge. Do you think it's capable or not capable? For this one. So the lower specification overlap with your lowest like outputs. Upper specification also overlap with your highest outputs. Do you think you're capable or not?
I feel like you're tricking us, so it's not capable.
Tricky?
I feel like you're tricking us because you skipped over it and went to the last.
Okay. So you are very good at customer behavior or psychology, right? So no. Okay. Yeah. This is very tricky, but I don't trick you guys. Well, the reason I come the last to this one is because this two is very obvious. Not capable. It's capable. This one, okay. Kayla can be right, even her logic can't agree because I trick you guys that it's not capable. It can be not capable, but some other people may think it's capable because it's really on the edge, right? But usually industry, we think it's not capable. We'll discuss that. Because industry think we still need to have a buffer area. This is too dangerous, right? To satisfy customer requirements, right? But I never trick you guys, except during Halloween maybe. Okay, how to calculate the capability index? So the CP is the capability index, is the upper tolerance limit minus the lower tolerance limit divided by 6 sigma. Sigma is the standard deviation of our process. So CP UCL minus UTL, also UCL. LTL divided by 6 sigma. Okay. So lower and upper low tolerance limits usually is raised by your customer or maybe your design department. They say that is our target. Sigma, you have to calculate by yourself. As an example here, a manager has the option to use any of 3 machines for a job, A, B, C. And the process and standard deviation are listed here. 0.13 millimeters for A, 0.08 millimeters for B, 0.16 mm for C. The customer, let's say the customer has a specific requirement of the wise is 0.8 mm. So we want to determine the capability index, which is CP, for each process, for each machine. So the specific wise is the range of the upper tolerance limits and the lower tolerance. So basically, you don't have to calculate this one. It's already given here. The numerator is 0.8 mm. That's the wise, right? Then you only need to do is divide by 6 sigma. Then you can calculate the process capability for A, B, and C. I'll give you guys 5 minutes. Should be more than enough.
Where are you going? Oh.
Then we'll discuss the criteria to see whether it's capable or not.
Yes. The width is like the range. So
Yes.
that would be the upper top. Subtract the lower top. So
They took the height, subtracted 0.08 from 0.67.
because this process in the range to be.
Yes. Yeah, for each one. 3 machines you have to calculate.
How much? I guess these are the one. Unless it's given out upper times.
sigma.
So 6 is just what we're using each time, no matter what, like
Yes.
0.13, 0.08, 0.16.
Yes.
Yeah,
6
so-
multiply.
So we have like 3 and
Yeah, because you need to calculate the capability for each machine.
Oh, okay.
Right, and then we'll discuss, okay, then who is capable to do our job?
And
Not all the machines capable.
Yeah, what's CP stand for?
Capability index,
Okay.
I don't know why CP. Capability, C and capability. Index, I don't know why P. Do you like your broken sentence?
I only know two because they sit right.
Lost? That's okay. So the y's, yes, is equal to, you don't have to calculate this because it's already given.
So
The y's is the gap between the upper tolerance and lower tolerance, right? So it's 0.8.
6 is this thing.
You only need to calculate this divided by 6 sigma. Well,
So
what
you
is sigma?
Plug that in and sigma in there.
Standard deviation. Right? So for each machine, we know the sigma. We just plug in.
Sigma.
That's pretty straightforward.
You don't have to do that one because 0.8 was already,
Antonio.
that would have a subtraction part, but it's
You
already.
definitely don't want to miss further class, and especially you have a case study with your team. You want to leave your contact information to them today, also get their contact information. And begin to do that as soon as you guys can.
Oh, wait. I did.
Sure, definitely. So, the 0.8 was given is in fact this difference, the y's. That means it will be the y's of this gap of the upper tolerance limit and the lower tolerance limit. So you don't need to worry about it. It's 0.8, okay. 6 sigma. What is sigma? Sigma is the standard deviation, right? For each machine, it's already given. So you just plug them in, you get 3 numbers. Right? No problem. It's my pleasure, always. Okay. Close.
If you don't win by 15, it's 20.
Trying to figure it out or not? You trying to figure it out? So we're using this equation right here. Going to
Took me. I'm sorry.
I get it.
Okay. I have seen many students have finished this question. So let's do it together. So for machine A, who can tell us how to calculate the capability index for machine A?
0.8
Anybody?
0.8
sigma.
0.8 divided by
6 times 0.13.
1.3. What's your result?
1.056. I want 1.02.
1.06, right? B would use the same thing, so equal to 0.8 divided by 6 times what? 0.08. You guess equal to what? 1.67. Great. And C 0.8 divided by 6 times 0.16. What is the final result? 0.8. Okay. I haven't tell you the criteria to determine what is capable. But so what do you think? For these 3 machines, If you can choose any of them, which one you will go?
1.6.
7. Very smart, Kayla. Why you want to go to a bigger one?
Because it's your capability, and the higher capability would be a better option.
Why? The higher the better. Can you
Producing.
look at this standard deviation? Right? B has lowest standard deviation, which means it's not just stable. Their performance is very, very stable compared to NSC. NSC are also very stable. They have this standard deviation. But B has lowest standard deviation. Because standard deviation, we calculate capability index is in the denominator. So the smaller of the standard deviation, the larger of this capability index. So Kayla is correct. The larger of this number, the better. Okay. Generally speaking, theoretically speaking, any number greater than 1 means you are capable. For these 3 sigma. Because this lower 3 sigma, upper 3 sigma, total is 6 sigma. Right? Think about for normal distribution, this 6 sigma already cover almost 99% of the occurrences. Anything above 1 is capable. If that's a criteria, we can choose which machines. Anything above 1,
A and B.
Top
A and B, both, right? But in reality, in practice, we have another magic number. The number is 1.33. This magic number, by practice, is that most companies use this number to determine whether they're capable. So basically, they want to leave a little bit of buffer area. Like the machine A, 1.03 is merely satisfy our requirement. So many companies don't like that. So in the practice, most companies choose 1.33. They only accept the process machine has the capability index above 1.33. If that's a criteria in practice, then B is our only choice to satisfy this requirement. Clear? So that's how we use this capability index to determine which process or machines are capable. Okay. Oh, if the process is not center as the target, which means okay, the customer require like 30 miles per gallon from 29 to 31. If that's the customer requirement, but you find your cars, the average is 29.5. So the average is already below the customer's requirements average. Then you can't directly use this formula. Well, this formula is only for the center position. If your process, the mean, is the same as the customer's requirements mean. If not, then we have to calculate the upper capability index and the lower capability index. To calculate this is also very straightforward. Upper tolerance limits minus x bar, which is the mean of your process, divided by 3 sigma. And the lower capability index is x bar minus lower tolerance limit divided by 3 sigma. And then you choose the minimum of these two values, you get CPK. Again, criteria is still the same. Okay, theoretically speaking, CPK greater than 1, capable. In practice, usually 1.33. But this will handle straight. Even in your center, you can use this formula too, right? But if it's not centered, basically your outputs mean is differ from the customer requirements. Same here, right? So then you have to use this formula. Rins?
So you're saying the capability index is normally like 1.32?
Yes.
Okay.
In practice, yeah. But well, anything we teach here can be different when you work for a company. Different company can be different criteria, but you just keep that as theoretic as 1. Maybe some company may accept 1 is now, but maybe some companies say we have a higher standard, we say 1.5. This can happen, right? But generally speaking, what we can teach you guys is that generally speaking, 1.33 is widely used for the capability. Okay. So how to improve the capability? To make it simple, standard, mistake-proof, upgrade the equipment. For example, parallel parking. Right nowadays, a lot of cars has the automatic parallel parking skill, so don't need to worry about how to park in Manhattan. Right, the machine can help you automate. Takuchi loss function. Takuchi is a Japanese professional in operations management. He has idea different with our traditional idea. Our traditional idea is that, okay, if customer tell us lower and upper specification is their tolerance range, then anything falling between this gap, we think customer happy. Right? Even it's very close to upper, very close to lower, customer happy. But once we pass this point, we have a big loss cost, complaints, customer switch to some other provider. So that's if we see loss function is 0 within this range and very high after we pass lower or upper specification. That's traditional one. Takuchi, he has a different idea. He think, okay, even we are within the range, but if we always very close to upper specification or lower specification, our customers still not happy. Well, they accept that, but they're not happy. You already have some cost here. Potential risk to lose the customer, complaints, right? So you already have the cost. Once you pass this limit, some customers say, okay, one time we accept that. So it's not so bad. It's not so bad to so high loss cost. It's gradual increase. So you can see the basic difference of the traditional view and the Takuchi's view is that whether you think about this tolerance is a strict one. Now sometimes it's strict. Okay, if you satisfy me, no matter how much you satisfy, I pay all. If you don't satisfy, you get nothing. Or some other customer different say, okay, I do prefer this range. But if you pass a little bit once per year or just a little bit, I can accept that. Or just charge you a little bit. The more you pass the criteria, I charge you more. So it's become continuous. So I believe both of these two ideas make sense. It really depends on your customers. I think customer is a hard customer, probably is a traditional one. But your customer is kind of easygoing, probably that's a continuous loss function. Okay. The last one is limitation of capability measures. The process may not be stable. Then it's really hard to calculate standard deviation. May not be normal dispute. No center, but we still use CP. Just pay attention here. If no center, we use CPK instead of CP. And definitely quality is very, very important for all the customers, products and service. And the last one is capability. We want to increase our capability. Even we think our process is under control, is stable, but stable doesn't mean too much nowadays. A customer has a higher and higher requirement. You can't say, I did that in business 10 years, right? We are very stable. That's our output. Some customers don't like that. Okay. I will finish the class early so you can get familiar with your teammates, leave the context message and discuss when you guys will meet, or maybe you have textbook you can think about which person cover like question 1, 2, 3, 4, 5 in your case. That's the end of the